the world, in the universe. We do these once a quarter. We alternate with Science on Tap and Arts on Tap, which also happen once a quarter on the other months. Ours is usually the first month of each quarter, and they're always on the first Thursday of the month. But I've heard a rumor that they may start changing to Monday. We'll find out, I suppose, in the next cycle. Yes?
There's a microphone startup so everybody can hear properly. If you guys want to just, 4 of you want to move over there, it's much bigger space over there for you to have to stand up.
Oh, so we should be standing over there instead of over here. We always stood over here before. Okay, this disrupts.
Whatever you want to do, Galen. If everybody can hear, whatever you want to do is fine. It's up to you.
Can everybody hear us? So, okay, all right. A little louder, okay. Hush. All right, we will stay here, but if anybody needs us to speak louder, please indicate, right? So I'm Galen Gissler. I don't usually organize these things. It's usually Jonathan Creel, but Jonathan is on a plane coming back from Costa Rica, so he asked me to give the announcements and all in his stead. I'm frequently here presenting for Nature on Tap, but tonight I have 3 guests with us. Jonas Lippener, did I pronounce that right? Sort of Aichin Aikutalt, which is much harder, but I think I got that right. And Jonah Miller. And these are all postdocs at Los Alamos National Laboratory, and they've been working very hard these last few months on a subject which interests me a great deal and has gotten a lot of attention in the press. Namely the collision of 2 neutron stars, which was detected by the gravitational wave detectors in Washington, Louisiana, and Italy last August, and first reported in October. We gave a couple of presentations on this subject at the planetarium at Peak, but this evening, we have an opportunity to have a more informal discussion about it. We won't have any fancy slides or handouts or anything like that. We will each of us talk about what most interests us about this particular event, and we will invite conversation. We'd like to hear people's questions about this. Also, if you have anything else on your mind in the realm of astronomy and astrophysics, please bring that up towards the end, and we'll try as best we can to field whatever questions and initiate further discussions. So with that, Jonas, would you like to start? Or actually, Jonah, talk about gravitational waves.
Okay, sure. So this is not the first gravitational wave event that we've seen. But what's partly exciting about it is it tells us that we can use gravitational waves the same way, in some sense, the same way that we use light to observe things in the universe and learn about them. So gravitational waves are ripples in space-time that come from the motion of stuff, heavy mass. And they travel at the speed of light, and they basically don't stop for anything. So they travel right through everything. And this lets us see what happens inside these neutron stars as at the very end when they merged. And also it lets us extract things about them that we would never learn otherwise, such as what were the masses of each neutron star? How far away were they? And they even helped us figure out where in the sky these stars were, because the gravitational waves, our detectors are able, with enough detectors, we're able to figure out via triangulation where in the sky they came from. So I think, I can talk a lot about why gravitational waves are really amazing and cool, but I think what's most exciting about them by far is that they're essentially a new telescope that we can use to look at the universe. So maybe I'll pass it to Aichin now.
Okay, sure. I don't actually work on the gravitational wave itself, but I work on the formation and the growth of supermassive black holes in the early universe. That doesn't only include the supermassive black holes, any scale, because a black hole is a...
You should talk a little slower and a little louder.
I will try. So, a black hole can form at any time in the history of the universe with any mass. and that makes them very interesting tool to study the evolution of the universe itself. So in that, I am theoretically working on the formation processes of black holes and how they grow and shape the evolution of the galaxies and the universe itself. In this, because black holes are black and you are looking at them at the black background, it was very hard for us to study them observationally up until now. With gravitational waves, it gives us very important details about their nature. That's why it is very important for us to detect them more, and which will allow us to understand their nature more, along with the nature of the universe itself.
Also, I haven't really looked at gravitational waves much. That's not my field, but my field is what's called nucleosynthesis. And so that's basically studying where all the elements that we observe nowadays, where they come from and where they were made. And so we know that at the Big Bang, only hydrogen and helium was produced, and then stars, they're fusing hydrogen together into helium. That's what the sun is doing right now. That's what provides the energy for it to shine. And then in more advanced stages of stellar evolution, once helium builds up in the core, and helium can be fused into carbon, and then you can make oxygen, neon, magnesium, and so on. You can make heavier and heavier elements, but you can only get to iron. Once the star builds up iron in its core, then it can no longer extract more energy from iron, because if you try to, like whenever you fuse lighter elements together, it releases energy, but with iron that process stops. So if you try to fuse iron with something else, you actually have to add energy to it. So it's sort of like the ash of nuclear burning, and you cannot get any more energy out. But then the question is, where do we get silver from that's heavier than iron, or gold, or uranium, or lead? And so all these elements, we observe them, they obviously exist. And up until fairly recently, we didn't really have a good, or we've had suspicions of where they are produced, and we know how they can be produced, but it's still been an open question of where exactly they are produced. And one of the leading candidates for where it happens is a neutron star merger. And so now that we finally observed one that we knew this was a neutron star merger, and then later we also saw signatures of heavy elements that were produced in this merger, we now know that these neutron star mergers, they create heavy elements like gold, silver, lead, uranium, and it is very possible that they are the main site or the only site where all these elements get produced. So it is possible that all the gold that exists in the universe was produced in neutron star mergers, and so that's pretty exciting. And for a very long time we've had this suspicion, but now we've sort of actually have data from this observation that corroborates those suspicions.
So this event that was observed on August the 17th of this year, last year, sorry, yes. Predicting the future, I'm not. So these three people here work on rather different fields: gravitational waves, black holes, and nucleosynthesis. And we have another person who I'd invited to come, but she wasn't able to, Nicole Lloyd-Ronning, who works on gamma ray bursts. All of these four things were manifested in this one single event, which is what really sparked my interest in it. That suddenly you have the potential synthesis of a broad range of astrophysical topics brought together in this one observation. The gravitational waves were detected, and then gamma rays were detected by a NASA satellite and an ESA satellite, and then it was followed by scores of detections in other wavelengths, including the optical and infrared and radio, which give us more and more information about this event and about the processes that we've been talking about. The whole story isn't yet in. In fact, I just heard this evening from Jonas that there are some new papers that have come out based on relatively new observations that will somehow change somewhat the interpretation of this thing. But what remains, absolutely rock solid is that here for the first time we know where for example, gold and platinum and iridium and all of these, and the rare earths were produced, at least one source, and we have a vindication of the gravitational wave detection technique, which now enables us to do astronomy in this new band, this new messenger. It's been called multi-messenger astronomy now, and finally we get to see also the formation for the first time of what seems to be a black hole. And for some time there was the possibility that the object that was formed from the merger of these two neutron stars was either a neutron star or a black hole, but now
It's more towards the black hole.
right.
And it would be the lightest black hole that
Yes.
we've ever observed.
So,
Right. So, Aijin, how many black holes do we know of in our galaxy?
in our galaxy. So we have the central one.
The big one.
Yes, which has a mass of 1 million times the solar, our sun. So it's at the center of our galaxy. There is a recent paper that there is an intermediate mass black hole close by as well. It's not
Right.
really confirmed. It's very hard because even the light cannot escape from black hole, so it's very hard to say for sure that there is a black hole. But we are generally, if there is a very massive black hole, you are looking at the orbits of the stars around them, because when they get close to the black hole, due to its very strong gravity, they speed up, and when they are away, they slow down. So from there, you can estimate the central source that's causing that acceleration in the orbit of the star, and you can calculate or like more or less whether there is a black hole or not.
And so then if we see that there's an object of a certain mass and we don't see any light, we just assume it's a black hole? Is that how it goes? Or?
No, it could be optically thick environment
Right.
that the radiation doesn't go through, so you cannot really say for sure for that, but you look at from which region that emission is coming from, if it is small enough, because black holes are compact objects, very compact objects, and they are gravitationally very strong, so it has to come from a very small region and very high luminosity radiation.
This is also how we knew that there were previous gravitational wave detections, and this is how we knew that they were black holes. It was the confirmation that they were black holes, in fact, because we knew that they came so close to each other in their orbit that the only thing that could be so massive and so small had to be a black hole.
So while there's a lull in the conversation, I want to point out that there is a sign-in sheet here that my wife is in charge of, and if anybody has come in late and hasn't signed up on the sign-in sheet, please do so. We'd like to keep a record of who comes to these things and get email addresses and so forth. I'd also like to introduce, for those of you who don't already know, I'm Steve Becker, who is a frequent presenter here, and also Rick Wallace, who is shy and sitting way down in the back. If you guys want to speak up on any subject, please do so.
Well, I've got a few things I could point out that's happening in the sky this month that might be of interest. This month is kind of unusual in that we have 2 full moons. We already had one on the first. And that was a supermoon where the moon was very close, about 221,600 miles away. And they have another supermoon at the end of the month, of all timings. And on the 31st, it being the second moon of the month, it's often called the blue moon. This one's going to be a very interesting blue moon because it's going to turn red because there'll be an eclipse of the moon. And red moon. And the eclipse will actually start for us here at 4:48 in the morning. So if you're an early riser, it's good. If you're not, well, then you got to see because the weather's like whether you're going to get up. Totality will be at 5:52 a.m. just before sunrise, and it'll be deepest into the eclipse at 6:30 in the morning, just about the time the sun's rising. So we won't see, the eclipse after the point that once the sun is up and the moon is set. So that's what's going on with the moon this month. On Saturday, about an hour before sunrise, if you go out looking for Jupiter, you'll find it's near 2 other objects. It's right next to Mars, only 0.3 of a degree apart, so that's less than a full moon width. There's also the star Alpha Libra that's nearby. You could joined by a straight line. So those are the things you can look out for this month for special activities.
And regarding the lunar eclipse, the astronomy club at the high school intends to observe it. So we will go down to Overlook Park at I think around 5:30 in the morning, and to the soccer fields, and we'll be out there watching the blue moon turn red.
Okay.
And so if folks want to join us, by all means, and you're hardy enough to get up that early in the morning, it'll be cold, but dress warmly.
Is that called the bloody moon?
Yes. Super bloody blue moon. Okay. There we go.
Now, depending what's in the atmosphere, the color of the moon can vary from bright red to yellow, yellowish, all the way to gray and almost invisible. So it'll be interesting to see what the atmosphere is like that morning if it's clear.
What's the date on that one again?
It's
31st.
the 31st. So it'll be Wednesday morning, early Wednesday morning, the 31st of January. So Rick, so Steve remarked that January has 2 full moons. So does March have 2 full moons, and that means that February has none.
Yeah.
That's just the way it works. That doesn't happen often, but it does sometimes. Does anybody have any questions about to ask about gravitational waves, nucleosynthesis? Oh yes, okay, all right, we'll go for it. Yes. Sorry?
Could you tell us the masses of how much the different elements were produced?
That's you.
So it's actually very difficult to say exactly how much mass is produced, but we can tell from the optical observations. You can make some estimates, but it is very model dependent. But it seems to be around a few percent of the mass of the sun. So that's the total amount of ejected that was ejected and got processed into heavy elements. And then of the individual elements, actually gold sits at a peak, so gold is much more abundant compared to other heavy elements, and actually platinum as well. And I forget the exact numbers now, but it was something like a few Earth masses of gold were produced, give or take like a factor of a few.
And how much is that worth in $1,000?
Well, I think if we got all this gold, the price of gold would be naturally less.
Yes. Right. You had a question.
Of the events that we might hope to observe with gravitational waves, was this a particularly big or fortuitous one? Is this in the middle of the range, or?
Sort of. So what was very fortuitous about this one is that it was very close, which meant that we got a lot of good information about it, despite the fact that it wasn't really pointed at us just right. So, for example, we mentioned that a gamma ray burst happened. That points, those basically, you only see them if they're pointing right at you. And this one was not pointed at us, and we saw it anyway. So it was really close. That said, we believe that in the future we're going to see a lot more of these. So it's special in the sense that it's the first, but it's not special in the sense that it's the only.
And people have been waiting for this for a long time. I mean, this was one of the motivations for building this network of gravitational wave detectors. You know, they saw the black hole mergers first, and that wasn't surprising because they were so very energetic and so distant. But the neutron star merger, which has been implicated in the nucleosynthesis of those heavy elements, has been long sought for, and so this event vindicated a lot of those speculations.
How far away?
So,
How
How
far
far
away?
away was that?
Oh,
40 megaparsecs.
yeah, something like that.
40 megaparsecs, so like 120 light years.
Within this galaxy.
Oh, 40,
Certainly, yes.
40
Yes.
No,
how many?
no,
Not within this
not
galaxy.
within
no.
this galaxy.
40 kiloparsecs?
40,
Mega.
Mega.
so
So,
millions of,
120
million light years. No, it was in a different galaxy, NGC 4993.
Something like that.
Yeah, there's a very cool image of this. Hubble captured a picture of the galaxy and the merger event, the afterglow of the merger event, which is essentially the radioactive decay of heavy elements produced. And it is almost outshining the galaxy, but you can see them both in the same Hubble picture. And Hubble took several pictures, and you can see the color change of the afterglow from the radioactive elements.
And this afterglow, it fades very quickly, so it's only visible, like, to sort of very obviously visible, as Jonas said, for maybe a week or so.
Yeah.
So it pops up, and then it's almost immediately gone again.
Yes.
So I was just wondering, how accurately, the 3 detectors, do they pinpoint where it's coming from? And also, I guess you said there's gamma, but were there other radio emissions in that area also?
Yes. So the 2 LIGO detectors, Hanford and Livingston, produced a long, narrow ellipse, which there were actually 2 segments of it, basically in the southern sky, and those error regions were far too large to search for the individual galaxies. Then